Well, I haven't been bothering to check the rule very much lately, but I have this final class enrollment form to turn in today. So I think I'll just go down here to make sure it's correct. And of course, we have 3 concurrent students, Mr. Riley, and they're not on this list because, and Mr. Guymon, and who's the other one? There's a few final points I'd like to take up today having to do with distillation processes, and first I was going to say a few words that some of you are particularly interested in and didn't quite understand at the end of the last period having to do with steam distillation economizers, or the so-called use of the principle of recompression for obtaining some additional steam requirements by flashing off some of the vapor from the stillage. So I extracted some pages out of a textbook having to do with heat transfer, and this little thing here I hope will clear up a little bit the principle of recompression of vapors. Well, you see over here, this discussion entitled thermal compression is primarily directed toward the application of evaporators or concentrators. And but anyway, the general definition there: recompressing a vapor to increase its temperature, the saturation temperature, and therefore permit its use for imparting heat, or its reuse for heating, is called thermal compression. And so the conditions for this, as indicated here, is where the steam is available at a pressure higher than that required in the evaporator. Now, in the evaporator here, that would be, we'd have to replace that for the still column, if we're talking about distillation economizer. While the recompression can be effected in a steam jet booster. Now, a steam jet booster or an ejector, steam jet ejector they're sometimes called, both have the same principle of functioning and essentially the same design. As I mentioned before, as we've I think mentioned, pointed out in connection with the field trip we had, that on the evaporator we have the vapors being condensed from the evaporator are primarily condensed in a so-called jet condenser, where a spray of water directly contacts the vapor coming off of the evaporator. But in addition, it is necessary to have what they call a steam jet ejector to remove the non-condensable gases in order to maintain the vacuum. Otherwise, the vacuum couldn't be maintained at the level desired. So the steam jet ejector is exactly similar to this design here, in which high pressure stream is run through a jet, and the pressure is converted into velocity through this constricted jet, and therefore is dropped in pressure. And so it can draw in then in the suction position here either vapors or gases. In the case of the evaporator, where we're trying to maintain the vacuum in the evaporator while we're pulling out non-condensable gases, dissolved air and so on. SO2, in the case of their operation down there, because they had a lot of SO2 in the juice to be concentrated. But And I might point out, though, that the main application of thermal compression in distillation, oh, excuse me, not in distillation, but in evaporation, is illustrated by this figure 1442 on the left, which shows the vapor recompressor over on the left here, which is put in there primarily, put in there entirely for the purpose of economizing on the heat or the steam required. So you're looking at that drawing here. You see the top of the, at the top of the evaporator body, there's a line goes over here to this ejector or a compressor. The bulk of the vapor, of course, would go on up to the condenser, which is not shown in the diagram. Or it would go, might go in, the vapor might go into the body of a second effect if it was two effect. So only a partial compression of the vapor off of the evaporator body, it goes through the jet ejector and is compressed, or goes through what they call a vapor thermal compressor, the thermal compressor. Now it's interesting to note, well, now maybe it's time to turn to the bottom of the right-hand page there where it refers to that drawing, figure 1444, where it says high-pressure steam is caused to expand in the nozzle, A, from which it issues at a high velocity into the mixing space, B. I think you'll recall from physics and maybe physical chemistry that if you have a fluid traveling at high velocity, either whether it's air or a liquid, there's a low pressure. Usually it induces a low pressure at the lateral. In other words, you can, I remember we used to have an experiment in elementary physics where they, I've forgotten how it was designed now, but where you blew air through a through a jet and it'd pull things in at the side, or it'd cause things to suck up against this little hole. It's the same principle that you use in the laboratory for drawing a vacuum with a water aspirator. You run a high velocity through a small jet and it draws vapor in, so you can get a moderate vacuum with a so-called water aspirator. Well, it's the same principle exactly. So in this case, of course, we're interested in drawing steam vapor into that mixing chamber where the low pressure exists. And so then this work of compression, as stated here, results from the conversion of the kinetic energy to high velocity mixture, the steam plus now the entrained vapor or gas. And then this is converted into a pressure head through the, I didn't read all that, the mixed vapors are compressed to the steam chest pressure P3 by going through this section D, the diffuser section. See, the diffuser section is what we saw in that diagram I had out last time. And so that's where the confusion arose, is how that could create the suction necessary to pull vapor in. So anyway, that's vapor at the low pressure P2, or the lowest pressure in the system, at the middle point here, is entrained and compressed to a higher pressure P3 at the expense of energy in the mode of steam. Now, this is only possible, of course, if you have high pressure steam available that has to be reduced anyway. This is frequently the case because typically the boiler pressure steam is the order 150 pounds per square inch or more. And Referring back then here to table 14.10, there's a little table here which shows the thermal compressor economy. Now this, of course, applies to an evaporator body such as the figure on the left, because it gives various values here for the steam chest pressure. Now the steam chest, of course, is what they mean is where the steam does the heating, or where the steam goes in around the tubes in the evaporator and imparts its heat energy to the liquid, so it'll boil and evaporate inside the tubes. Now, and so and it makes the assumption that the entrained vapors are given off of 15 pounds per square inch, or approximately 1 atmosphere. No, 15 pounds per square inch gauge, or about 1 atmosphere above 1 atmosphere above atmospheric pressure. Now, it shows here the entrainment ratio, pounds of entrained vapor per pound of live steam. And if this recompressed vapor is going to be applied at 18 pounds per square inch, and where it's only been drawn off at 15, it only has to be compressed 3 pounds per square inch to get an entrainment ratio of 3.33 per pound of live steam. Actually, that amount of live steam saved in percent, that's an incorrect value there, because I checked it out myself. It's a typographical error, because that should be 77%. In other words, the way you would get that, the way you get that percent saving would be that pounds of entrained vapor is equal to 3.33 per pound of motive steam so the total steam required is the sum of the two. Total steam required 4.33 so the percent saved would be equal to 3.33 divided by 4.33, and I believe that's 77%, or thereabouts. The rest of the values are correct. For example, if you had to use the steam at 20 pounds per square inch gauge, you save about 2 pounds per pound of entrained vapor. So in this case, you'd have 2 over 2 plus 3. Well, that'd be 2 plus 1 would be 3, and you're saving 2, so that's a 67%, or 2/3 saving, you see. Well, those are pretty significant savings, and so thermal compression is fairly widely used in evaporator industries, or industries requiring evaporation, particularly in those in which you only have, for other reasons, the option of using only 1 or possibly 2 effects. Why would you be limited in some cases to only using 1 effect instead of 3 or 4 modal effect? Let me go back. I really haven't systematically talked about evaporation, but since we've had a little bit of exposure to it, and it has some implications in our distillation discussion. First of all, let me say that if you have a multiple effect evaporator, did I ever show you what that looks like? Well, okay, I'm getting off on a tangent now for sure if I get into this, but I'll do it. For example, if you have, let's draw a little sketch of a single effect evaporator. Well, in a simple case, it'd look like we'll draw something here that represents an evaporator body. There words, I'm saying this is the steam chest here. This would be one style where the steam chest is down at the bottom and depend on maybe natural circulation. The one we saw down at Lodi, the steam chest was off separately here and simply had a pump circulating it back and forth. But in principle, it doesn't make any difference. So the vapor would go off here and go to a what you might call a jet condenser. Where water goes in here and is sprayed out through nozzles, so that or nozzles or a nozzle, so that the vapor is directly entrained with the cold water. However, it's usually not sufficient to. Well, anyway, and then this delivers in what's called a hot well. And if you don't have some pumping arrangement here, well then this section here is called the barometric leg. And it's about 30, it has to be around 34 feet above the liquid level if you want to get anywhere near atmosphere, a low vacuum. Because the pressure of the atmosphere is sufficient to push up a column of water, to 34 feet and 34 feet. So the atmospheric pressure, of course, exerts itself onto this hot well, and if you have a vacuum inside here, well, it'll push the liquid level up till the point at which the pressure on this and the pressure on there is balanced, and so in order to get the water to flow out from the jet condenser by gravity, well, then you have to have a 30 or 34 feet of clearance there for this so-called barometric leg that will operate. Not all evaporators are arranged this way. Sometimes they don't have this barometric leg, but they have to have a pump then to pump it away because it won't flow out. If you only have, let's say, 10 feet here, well, you have to pump it out if you're going to have a low vacuum. In addition to this, then, we might have a so-called jet ejector here, which I'm just going to say, I'm not going to try to draw it because it'd be exactly what this little diagram here is on your handout. Jet ejector. And there'd be motive steam going in here. And this entrains this non-condensable gases. And usually there's another hot well down here, or this tube here delivers into this one or the other. Now, I didn't show any vapor recompression here, but if you put one of these ejectors over here and ran the steam through that and made a connection down to that, well, you'd have vapor recompression in this too, you see. You'd have vapor recompression here. I'll just crudely illustrate this. This would be a vapor recompressor. Here'd be a motive steam. And you might or might not use that. Now, if we had a multiple effect system, and I'll just do that very, very crudely. Let's say here represents a triple effect evaporator. And these are the steam chests down at the bottom here, illustrated like so. And so we can have, so the principle is that if we introduce live steam into the first effect, we take off vapor, and if this pressure here is lower, so we have a lower boiling temperature, we can reuse that vapor in the second effect. Similarly, we can take the vapor off this effect and use that to reheat the third effect, which has to be at a still lower pressure or a lower boiling point. And and of course, then finally, the vapor off this would go to a condenser, like this, condenser and hot well. Well, the point is that the purpose of a multiple effect, this would be a triple effect evaporator, is heat economy only. When we're dealing with water solutions to be evaporated, we essentially get 1 pound of water evaporated for each pound of steam condensed. Because the heat of vaporization of water, that is of steam, is around 970 to 990 BTUs per pound. Depends a little on the pressure, but it's not critically dependent on the pressure. So from a practical standpoint, you tend to get 1 pound of water evaporated per pound of steam consumed in the first effect, or in a single effect. Now, if you have a triple effect, and you can reuse this steam by operating this evaporator body at a lower pressure and therefore a lower boiling point, you'll get another pound, essentially another pound of steam evaporated. And similarly in the third effect, you get another pound evaporated. So here you get an economy of only requiring 1 pound of steam for 3 pounds of vapor evaporated. But without going into any great detail here, it's obvious then that you have to have a fairly high pressure in this, or a high boiling point in reference to this. Otherwise, you're not going to get have any boiling point difference in this vapor than the boiling point in here. So you've got to so this has to be at a lower pressure than this one, and this has to be a still lower pressure. And in practice, these pressures have to differ by the order of at least several pounds per square inch, just as a rough guide. So even though we may not be able to operate this at let's say 2 or 3 pounds per square inch absolute, you'll likely have above atmospheric pressure over here. And so you have the problem of, with respect to organic materials and food materials, of thermal degradation of the flavors and components in the food materials. So that's the reason why we're pretty much limited to single effect, or sometimes new special designs whereby they have a very short, maybe that's a very short holding time. In other words, the damage done, of course, is a function of temperature and holding time. So if you can design an evaporator that can operate at maybe a higher temperature but a very short time, you may have no more damage than you would be at a lower temperature in a more conventional evaporating system. So anyway, theoretically, you could put a vapor compressor on this here. But since you're going to reuse the vapor anyway, well, there isn't too much advantage in doing it here in a multiple effect. But there's considerable advantage in doing it in a single effect, because as this indicates here, you may be able to get as much as 2/3 of this, 3/4 of the steam saved. All right, now that leads me up to the point I wanted to make about, aside from giving an understanding of how this works. How much do you think would be a reasonable saving possible in a distillation economizer, as was indicated? Do you imagine we can save 77% of the steam, or even 50%? Anybody have any reasons why this same principle wouldn't apply to a distillation economizer, or why it might not? No responses, huh? Yeah.
One of the problems is you don't want to recover the vapor off the form of product that goes to the condenser. You certainly want to reinject that, because you'll never get the darn fluid out of the thing. So you're limited more or less to recovering the heat out of the bottom. And the bottom, being a liquid, don't contain a heck of a lot of heat.
Well, you're touching on it now. When we're talking about distillation economizer, we're talking about recovery of some of the heat energy that's simply sensible heat of the liquid, of the bottoms. Because there's no point at which we're drawing out vapor out of the distilling column to recompress. In other words, in its simplest form, if this represents the bottom here, and this would be the liquid level, and here would be our schematic representation of our thermal compressor, where we run in Modi steam here, and well, you got a better drawing than I can make of it here. But anyway, the stillage, which goes in here. Now, where's that drawing? Where's the copy of that? I don't have one. I don't have one of them with me. Here, let me look at that a minute. This one. This thing here is a. Let's draw it the way it's shown here. We got this. And so we have up here this tank, and Modi steam coming in here, and we'll just simply indicate it like this, and that there's that the stillage goes in. Stillage comes out here and goes in here somewhere, and then comes out here. Anyway, this stillage here has a temperature as it leaves the still of somewhere 212 or higher. It'll always be a little bit higher depending on the base pressure. So the temperature might be, for example, 220 degrees Fahrenheit. So the question I was asked here, so is there some limitation on the amount of vapor we could flash off of this boiling liquid in reference to the amount of steam supplied here? Well, the answer is yes, because the only heat available for heat economizing is the sensible heat of this liquid. There's no vapor heat of vaporization available as it starts out. So we can only get this energy by reducing the pressure and causing it to flash into a vapor. And of course, as it flashes into vapor, it takes off the heat of vaporization of water. And so therefore, the pressure is brought down to whatever, or the pressure has to be brought down to some value which will flash. And, this has some practical limits.
Did you say you could only get energy from the liquid going to the vapor?
Well, the only energy available for heat economy here is what energy is in this stillage going out.
I don't see why the liquid would go into a vapor unless you could...
Because you're reducing the pressure on it of a saturated vapor. You're reducing the pressure by bringing it into this economizer.
Well, you're putting it in there with the steam, right?
No, you're putting it in as a liquid, but you convert part of it into steam by dropping the pressure. It's another example of it's sort of an example of flash distillation, if you want to think of it that way, although we didn't treat it from this standpoint. But you're flashing a liquid into a vapor by dropping the pressure. At some reduced pressure, this stillage here, which has a saturation temperature of 220 degrees Fahrenheit, because it has about 3 pounds per square inch gauge pressure at the base, as a typical case. When it's reduced down to some pressure, maybe as low as if the temperature might get down to 175 degrees Fahrenheit, we can look up what the pressure would be, saturation pressure, by looking up steam tables. So let's see what that is here. For 220 degrees Fahrenheit, the pressure is 17.2 pounds per square inch absolute, or about 3 pounds per square inch, see? Just what I said. If you can drop the temperature down to 175, or by lowering the pressure to about 6.6, roughly 6.6 or 6.7 pounds per square inch, absolute, or a vacuum of around about 14.7 minus 6.7 would be 8 pounds per square inch of vacuum, or negative pressure, you could say it that way. Or you can vaporize it. As a matter of fact, if you drop the pressure down to this point, the temperature cannot exceed 175. It'll evaporate until it drops the temperature down to 175, to the saturation temperature of water, considering the tillage as water, essentially. So, consider also that this stillage going out, if we want to say 175 degrees here, leaving the economizer, is still going to be utilized in a conventional type heat exchanger for feed preheater. And I won't show the feed preheater. The feed goes in up here. So if this goes in at only 175, we're going to be, and we want to get, let's say, 140 to 150 degrees out of that. We can't have it much lower than that, or we won't have any preheat available. I won't have the opportunity for preheating the liquid. So not much point in dropping below that, even if we could. If you want to drop it down to 120 degrees Fahrenheit, which might be a reasonable discharge temperature, how low a pressure would you have to get? Well, it'd be almost impractical to get. It'd be impossible to get it. Be impractical and also impossible. 1.7 pounds per square inch, absolute. So you can't obtain that in these type of devices. Now I took the problem, what did I do it? I took the situations for that problem that we used as an illustrative handout last time, where we had a bottoms rate given on the table associated with the problem, and a vapor or feed rate. And it comes out to be that the liquid to steam ratio is about 5.67 to 1 in that problem. In other words, that the in that illustrative problem, I think it was March 6th, I don't know, something like that. We had the bottoms rate was 7,910 moles per hour, which is about 142,400 pounds per hour. Incidentally, the feed rate, which we don't need here, but was about 6,700 moles per hour. I forgot how many pounds that was, but it was, you see, somewhat less than the bottoms rate because of the condensing steam that we had because of the temperature of the feed. But anyway, what we're interested in, the steam requirement was 1,396 moles per hour, which is equal to about 25,150 pounds per hour. All right, now, the manufacturers of these devices claim that you can save about 25% of the steam requirement for heating. So making that assumption, I just worked out to see what this exhaust temperature would be, and it came out to be about 175, which is quite reasonable. For example, if savings of 25% are realized, why then we'd have 25,000. I think I worked the wrong. I had 25,150 times 0.25, and I think I used 500 here. But anyway, about 6,300 pounds of water are flashed into vapor, and therefore join the stream of steam. So the approximate heat of vaporization is about 1,000. It's a little less than 1,000, but I just use 1,000 BTUs per pound. So now you can calculate what the exhaust temperature of the remaining stillage would be by writing a little heat balance, and we'll say that 142,000 pounds of stillage times its initial temperature, 220, minus the exhaust temperature, times the specific heat, BTUs per pound, which we'll say is essentially 1, has to be equal to the amount of heat required to create this many pounds of vapor, 6,300 times 1,000. And so if you solve here for a T2, it comes out to be about 175 degrees Fahrenheit. So in other words, the claim of 25% savings seems realistic. But if you would work out any savings of the order of 67 or 75%, as was possible with evaporators, it would be an unrealistically attainable objective, because you can't lower the stillage temperature that low.
What do they use to lower the steam pressure to the venting this thing? Or they
course, and I must say these are not universally used, but it appears to be a good answer to some steam economy, and that's going to be more important in the future than it has been in the past, of course, with the energy crisis we have. But anyway, what happens is that when you normally you just bring the boiler pressure steam through a reducing valve and reduce it down. Now, of course, what happens theoretically is that if that's saturated steam coming from the boiler, when you drop the pressure suddenly, and it undergoes what's called adiabatic expansion, where you get a certain amount of superheat. In other words, there'll be that energy will still be retained, so that the vapor going into the bottom of the column may be slightly superheated or a slightly higher temperature than the pressure at the base of the still. But if so, it'll just help vaporize a little bit more of that liquid, so it'll soon come right back, down to the saturation temperature. Question?
Yeah. What does the motor steam do, and where does it go up there?
In this? In this?
Yeah. Does it go in with the stillage before it goes?
No, it doesn't. In this case, it doesn't go into the stillage at all. It simply goes into goes in here, and the vapor that's sucked off, flashed off of this stillage comes down through that little dotted pipe coming down through there, and that's where it mixes with the ejector.
The diagram isn't real clear as to which stuff to which.
No, the diagram is a little bit confusing. It's how it looks on the outside, not how it looks on the inside.
What's the line going over between?
This?
Yeah.
Well, this wasn't a very carefully drawn, this is a very crude sketch, but this represents the stillage going out here, and the stillage going in here, and this represents the steam going in. This represents the steam going into the still, which includes the motive steam plus whatever is flashed off and mixed with it. Right? Mm-hmm. Well, I had 3 or 4 other topics I intended to talk about today. To conclude fractional distillation, here I only got over 1 point, and maybe not completely that. Anyway, let me hand out this little handout here, and just briefly refer to what it's about. There's a little handout showing 3 flow diagrams for different. I guess there's four diagrams for different arrangements of continuous distilling units. You'll notice that the first one is labeled D. So it was actually part of a little report that I prepared where A, B, and C were other designs, but they're the ones we're already familiar with, like a single column and then a split column. And well, A and B were single columns with different arrangements. So anyway, I want to mention that these are some of the patterns of distillation columns that are actually in use in the wine industry in California. It's not necessarily for beverage brandy, although some would be, and some would be simply used only for drawing off wine spirit. But in principle, about the only difference in the 2 distilling processes would be that in the concentrating section here, the P, or the product, would be drawn off at the lower point in the column for beverage brandy, and be unlikely that there'd be a fusel oil stream drawn off here from the concentrating section. But anyway, this pattern D illustrates the combination of a primary concentrating and a stripping and concentrating column arranged as a split column, in which the main product is drawn off from the concentrating section as a side stream, and appreciable heads cut is taken from the top of the condenser and then fed into a separate heads concentrating column, which has its own stripping section and concentrating section. So from the top of the heads column, of course, so the concentrated heads is removed, and the bulk of the alcohol has to be taken off somewhere in that column and returned back into the system. the way I shown it here, it comes out with the bottoms. Now, it'd be possible to draw it off at some other plate level in here and recycle it back into the system. But anyway, the open steam can be used in the heads column. The and the other feature is that only a portion of the overall alcohol in the feed was redistilled as heads. Whereas the next drawing, we're briefly referring to, is an alternative arrangement that's sometimes used, in which there's no attempt to separate heads from the primary concentrating column, but rather the product is taken over the top as a top product, then fed into an aldehyde, what I call a separating column, from which heads are taken off the top, and the bulk of the alcohol comes out the bottom. And so, in order to avoid the diluting effect of steam, a reboiler is necessary, or indirect heat exchanger. So in this case, all of the main product traverses the aldehyde column. There will be very little change in concentration under practical conditions of the alcohol from the material that's fed into this heads column compared to what comes out the bottom, because the volume of concentrated heads taken off is relatively small. Might be at the most 1% of the bottom product, something around order of magnitude. And so you could write a material balance and figure out what the proof of the bottom product was if you know the proof of the feed material and what the relative volumes of the top product and bottom product were. But if you say we're making high proof and fed it at 192 proof, and the concentrated heads comes off maybe at 193 proof, the bottom's product would come out and be only a fraction of a proof less, or maybe 191.8 or something like that. If you're feeding in beverage brandy at 170 proof and taking off a heads cut at 193 proof, well, then there might be as much as a point of, be a little bit larger drop in proof going out the bottoms in past the reboiler. But it wouldn't be very significant either. Finally, last, no, not quite the last, but the figure F shows another design that was used in that very large column I referred to last time. Showed a little drawing of it, of the one down in Madeira, which incidentally had 70 plates total in the column, not 70 plates in the stripping section, as the concentrating section, as I read off. But in other words, it had 20. That particular big column had 20 plates in the stripping section and 50 in the concentrating section. But anyway, the way they handle the aldehydes is take off a side stream product and then run it into an aldehyde stripping column and take it out the bottom in the same style as in the previous drawing. But instead of having a separate concentrating column and condenser for the aldehyde column, they run the vapor back into the top of the primary column. Now, as I've indicated before, I think this is a rather faulty concept as far as separating aldehydes is concerned. It saves a little bit on water, condensers and so on, but I don't think it really is very effective in removing aldehydes. And finally, G is a principle that's not used in the wine industry so much, or at all, as far as I know, but is used in other distilling industries, particularly rum, and in essence the whiskey or grain spirits, where the material to be distilled is run into a beer column or stripping column, and may have 2 or 3 or 4 concentrating plates at the top, or may not have any. And the way the drawing shows, it doesn't really have any. But anyway, the vapor is condensed, and it's called low wines. And it shows a little low wine surge tank or accumulator tank here, which is then fed into an intermediate column where heads are taken off the top, but the bulk of the alcohol comes out the bottom as a relatively dilute material. The low wines, for example, could be anywhere from 40 to 60% alcohol, or 65, something like that. If you have enough plates, of course, the heads will come off at 192 or thereabouts. So the purified low wines comes out the base, would be somewhat reduced in strength, in proportion to the amount of heads taken off and the amount of alcohol removed there. But anyway, it may come out to be 40% alcohol, 80 proof. Then that's fed into the primary concentrating column, where the primary product could be drawn off as a side stream, and the light heads taken and recycled back perhaps into the purifying column, not shown here on the drawing, and a conventional bottoms product taken out. This is a fairly good design from the standpoint of removing aldehydes, because aldehydes are more effectively removed from dilute alcohol solutions or from water than it is from high concentration of alcohol. So the disadvantage of this is that all three columns require their own heat supply. You have to supply steam to all three columns. This principle is extended a little bit further in the designs like was illustrated in that handout I gave of having to do with grain distillery operations, where it showed an extractive distillation column. Now that sort of corresponds in principle to the purifying column, where low wines is run in, but the alcohol content on the trays on the column, called an extractive column, are kept much lower by actually introducing boiling water up at the top level and diluting it. So you dilute it down so far that not only the heads are more volatile, but the high boilers are also more volatile, and they come off in the heads also. Fusel oil and the fatty acids and fatty acid esters and so forth. So I guess that's a little past time, so I'll stop there.